Today, we get to look at Jeffrey-Hamel flow. It's my favorite solution, favorite analysis of fluids, I think, just because it shows you everything, I think. So today, I'm not even going to look at time. I'm just going to continually talk about Jeffrey-Hamel flow until I'm satisfied. And the bigger point of this whole lecture is I'm trying to show you how this is my favorite solution. So I think all of you, because you saw a bunch of methods, I think it's most helpful to pick your favorite solution. I showed you a bunch of examples, but just maybe try to like one of them, right? So in this world of fluid analysis, I think it helps if you have a favorite. So mine's Jeffrey-Hamel. And then, when you're trying to think about methods of fluid analysis, just look at your favorite solution over and over and over again. And then use that one problem to just test all of the techniques and methods on. So then just resolve it over and over and over again using any methods, all the methods that we go over in the class. So I like Jeffrey-Hamel flow because in my mind it has almost everything involved in it, right? So I think this solution has great scaling arguments when it comes to a wall variable. It's also radial. What else does it have? It's also a radial problem. So it's a radial problem, and I struggle with radial stuff a lot, so I like to look at it for that because maybe it'll help me get better at radial flows. It also has, it's also sort of a nice nonlinear ODE to, let's say, test your numeric methods on once you have it. Sort of like homework 1, only you can just kind of do different sort of integrations on this. Jeffrey-Hamel flow, this solution also shows, just all the great analytical methods are in this solution as well. What else does it have? It's really it has great asymptotic analysis in there as well. A great boundary layer problem, meaning there's a boundary layer at really fast flows you can get analysis. You can sort of look at through this problem context as well. And even a mathematical boundary layer pops up in it as well. Essentially, you have a small term in front of their highest order derivative term in your differential equation. That's in there as well. What else do we have? Jeffrey-Hamel and growth. I like to use it, too, because it has something called elliptic integrals pop up in there. And, well, I don't really need a point on this, but it's me in my world of math. I like to use Jeffrey-Hamel flow and look at the solution and see how these elliptic integral functions are defined and where they really come in handy for. What else can I find in this solution? Elliptic integrals are in there. You got boundary layer problem, asymptotics, nonlinear ODE, scaling. It's radial. What else have I found in here as well? You can keep going and going on and on and on. Oh, it's got an integral. It even has has an integral boundary condition, which you don't usually see that often. So sometimes this is referred to actually as an integro differential equation. So again, you don't really have to do it that way for Jeffrey Hamel, but it again illuminates how these things can pop up or what an integral boundary condition really ends up being. What else does Jeffrey Hamel flow have? It's got the integral, so many things in the solution. Integral boundary layers conditions, asymptotics, one-weak integrals. I think just like has a great great integral methods, right? So like what you see, right, the analytical solution ends up being an implicit integral, and that's where this definition pops up. But even before you even have this, right, I like it because like it has just kind of I can just like rederive things if I just like look at the condition of this quadratic term in there. So it just sort of shows how it's really amazing to just kind of see the same thing over and over again. You can really test integrals out, or just like really analytical methods. They're all in here as well. What was another one I thought about that's in the solution? I think of the boundary layers. It's got an integral boundary condition, asymptotics. This one's important because this is like really, I'm really going to kind of show you what this stuff is, because we're going to look at like small Reynolds or large Reynolds effects on the solution. So it's kind of a natural sort of introduction to where this thing comes in handy. Scaling arguments are nice too, because you show how you have to do like a argument as well. This boundary layer, you have like wall variables. So if you remember for these plate things, we had like, well, I couldn't satisfy no slip. That's in there as well. It just has, it's in an angular form, so it's pretty nice that way. I keep finding things in it too, really. That's the other best part of it. I call it the coolest solution ever. It's like listening to your favorite record on repeat with like really nice headphones, and you're just like in the zone, the notes for this, honestly, the notes for this lecture I just picked out a bunch of, notes I've had that I've made over the years. I have something about like 3 pads of nicely written engineering pad work paper of me just redoing Jeffrey Hamel over and over again. So I really just kind of peeled pages out of there to make a lecture for Jeffrey Hamel flow. But the point being, you don't have to pick Jeffrey Hamel flow. This one's my favorite. I think more importantly, maybe, I want you to just see how I can take one solution, right, one method of getting at what this velocity field is, and how myself personally, I like to just sort of redo it over and over again and just affirm the techniques in my own head using one of my favorite problems. So again, my favorite's Jeffrey Hamel flow, but all of the ones I've showed you, all of the examples I showed you, right, maybe you didn't get them the first time, and no one's going to get them the first time. But if you liked one of them, then maybe just like make that your favorite one, and just like keep on working it over and over and over again. And that's really how you can solidify all of these methods, I think. So if you, the idea is we have a storage issue as humans, I think. We can't know every single solution and all the details of every single fluid solution that's out there. But you can pick one, right? And then when you hear these things, you go like, oh, asymptotic, oh, that's in the Jeffrey Hamel flow. I do the one thing. Okay, yeah. So that's what I'm trying to get across. And that's why I'm just going to talk forever and ever and ever on Jeffrey Hamel flow, because it's a super neat solution. Okay, so what is Jeffrey Hamel flow? Well, I've said before, to start any sort of fluid problem, right, you should draw like what do you try to model, right? So Jeffrey Hamel flow considers flow in a wedge. Okay? And it has really cool, I should have said that, like, it's really good analysis for like, I like the solution too because it's good analysis to show you how like algebraic sign is just a pain in the ass sometimes. So maybe put that down in the notes of why I also like this one because it shows like a clear dependence of how like algebraic sign can totally change how a solution behaves. We will see that. Okay, so here is a converging wedge. You can think of it as converging or diverging wedge. There's some sort of point source right here, right? And more importantly, besides some suction or expansion of flow, you more think about just flow rate going into or out of this wedge, right? So you could have some radial like this. And then you have these scenarios where, well, I could have the flow going in or going out. So I have flow going in or out of this converging or diverging wedge channel. So commonly in Jeffrey-Hamel flow, right, we say that inflow is negative, and then the outflow is a positive case. So it's good to just say that right now. And again, you got to really appreciate how these things can become pretty important. What else about Jeffrey-Hamel flow? So it's a radial system first. That's the other important thing, because one of the better things about how I'm going to try to describe this is, well, I'll draw my center axis here. Try to do it well. If I'm trying to look at this flow, well, I can start this point source right here, and I will draw my axis like here. This will be my radial axis coordinate. Okay? And that makes the sweeping angular one is almost in place of my u of y, but now it's a u of theta, because if I change this angle, right, that's where I want to pinpoint or try to find what the velocity is in the wedge itself. Again, just remember that we have outflow, right? Outflow is a positive case, or it's parallel in line with the radius going outward from my point. Then inflow being the negative course, negative because I'm going in the direction to this point source right here. Okay. So now we label, right? So if I have this is right, and I just now got to start labeling some geometric terms. For Jeffrey-Hamel flow, we have half wedges because there's a symmetry, and we assume some sort of symmetry here. So the wedge angle will be alpha. Is it half wedge? Yeah, so that's going to be the half wedge angle. That doesn't quite matter, but for a scale sense, you can also think of how there's some distance, right, of the plate. So from here to here, I have some script L talking about the length of my converging or diverging plates into this flow. Okay, and then we have the z-axis going in and out of the board. So you could even call that W, right? So it could be like a really deep channel. So this would be the width. Just in and out of the board. Okay, and then for Jeffrey-Hamel, right, we make a 2D assumption, and the 2D assumption being that the scale of the in and out, right, the scale of the in and out goes to infinity, or you just say that it's non-changing, or there's no pressure gradients in or out of this board to cause any change in velocity fields. I don't have any effect, I don't have any energy I don't have any pressure gradients to cause any sort of change in fluid velocity lines in and out of the page. You also just do it from just, a 2D flow assumption. Okay, so what you're getting at with this type of a setup, right, is I want to draw some sort of, right, if I go anywhere out here, right, what's the velocity like? So that's what we're going to get at in Jeffrey-Hamel flow. If I sweep up at some angle here, and then maybe at any arbitrary radius value, what's the velocity there? Is it going in the right? Is it radial? Is it radial? Is it angular? But sort of being able to find any sort of velocity value at this point. Jeffrey-Hamel flow, we also make a steady state assumption. Okay, steady state assumption being the time rate of change. The operator is really the 0 one. But in a scale sense, again, you can do the same thing. Going, well, if I'm looking at just I'm looking at very long time scales. So I'm having some sort of time scale, capital T, that goes to infinity. So in all those terms will also kill off in your scale sense as well. Half angle edge, and we have some velocities. Okay. So one issue is about here, right, if I have some sort of flow rate happening, is we do have an issue with Jeffrey-Hamel flow of this infinite point source. Okay? So if this flow rate's supposed to be conserved, I have some area here, and then this would have to equal this one as well right here. So you can see at the flow rate right here, I need to have some infinite velocity because I have now a 0 amount of area right there. Right? AV, right? AV here equals AV there. So they have a ratio of velocities. I have a 1 over, right? I'll have a 1 over 0 area relationship. So that means that that velocity would have to blow up to infinity. So for when you use Jeffrey-Hamel flow, it's also good to realize there's a limitation that you can't have. You don't really want to consider this actual point source, but it's an idealization that all the flow, incoming or outgoing, is coming from some infinite point source. But then the viscous parts of here are so close together, right? My walls are so intermediately close together that even if it is really close, all of the viscous forces right there will dampen that out, and then you will mostly get the velocity field that you have in the solution. But just in case, right, for the solution, you really cut off to some sort of minimum radius here, or length of radius. Right, so then that kind of says that I have it's a radial coordinate, right, and this will belong, think of it as like 0, not including the 0, and then some capital L. So just don't include the 0, really, right? You could just actually put some sort of epsilon here saying, I really only care about like a really tiny, like little tiny infinitesimal bit in front of there. It just kind of fixes one point. And also important here, you'll see that it's important that you don't include the 0 point, or you don't include this point here. Okay, on our way. So that's a picture. So this really being the 2D assumption. (2D) is really coming from this assumption that this W scale blows up to infinity, and then the steady state assumption being coming from here. Sort of, where do you go from there? Well, right, then you go from there. Well, now it's time to start plugging things in. Right, so now, in this situation, let's move into the continuity equations. Okay, so continuity, I have a nice picture derived right here. And what is my velocity field, right? So here's my velocity field in general, right? Right? Keeping that in the general case. So this is a velocity vector field, and these are scalar components of what all the velocity, right? All of the field velocity that's happening inside of this wedge with flow occurring. In general, I have this. Okay. So then, in the radial sense, let's look at the gradient. It has this definition. You look it up. Boom. And then this just keeps as a z. Okay, so this is my general velocity field right here. And then right here, I'm just defining right now what's the gradient operator look like in radial coordinate systems, or cylindrical, because that's what I'm having. So I'm writing down here. This is not a v, right? This is my nabla operator. Okay, so now just starting from here, here's where I then put the scales in. Right? I don't have no idea where I'm headed with this problem right here, but then I like to go like, okay, I have some relationships in terms of geometry. I could have that the W, right, L. You could more so just have that the L is much, much less than the W. So now I'll insert those scales, okay, or just start defining this. So my non-dimensional angle, not too hard to just come up with that, right? I just normalize by the only angular coordinate I have, this wedge angle. Nice to have. R star, what do you got there? Well, again, not that rough. I have my R going from like not really to 0, but then it's bounded by here. So then that dimension is going to be the total length of the channel. And then I have, and make this one the width. So you could just say 2D, right? You could just say 2D immediately. But if there's a scale situation like this, you do so, right? If you use some sort of scale, you can go like, okay, well then that means that this one will die out, this operator dies out because the scale is too large, or you could say that Vz is just 0. Okay. So that being said, so sort of with these just scales right here, I go like, well, that's certainly not too bad. This one's maybe a pretty small number as well, so this one's going to matter. Okay. And then this Z1, I just go, okay, that's going to not matter anymore. So essentially getting rid of that. And that just really kills this in one argument. You also could just say that that the velocity in this direction is 0. And the only way that would be 0 is if you don't have a pressure gradient right there. So then in the problem, you could just say, it's not really a pressure gradient there. There's no driving pressure gradient in the z direction, so there can't be a velocity. Remember that pressure, right? You need to have some pressure to cause some sort of motion, right? You can't scale the pressure away. So you have these two arguments. I could either have I could have infinitely larger into the board. That's really the best way to do these things. Or you just know that you don't have a pressure gradient in the z directions. So that gets rid of this one. Okay. So then, just after inserting these scales, now we have this. Okay, so now I immediately see from my operator now, once I plug this into any Navier-Stokes equations, I immediately just throw away the z coordinate, or throw away that z momentum equation in these. Now coming from this argument here where I have an infinite w scale. It's important to say that one's 0. This operator on any v now, it just neglects now that z term. And then right here, what I've just said is s is just the arc length, right? Because right, alpha times L is this arc length. So then with here saying, right, it's just the arc length of this sweeping angular velocity. Okay, it's not too bad, pretty good. Okay. So so all this is say, right, by drawing this picture and saying that w going really infinite, what I've said is like, okay, well, I'm not going to care about that z velocity. So really the vector field I'm looking for, right, my approximation to the Navier-Stokes solutions is 2D in the sense that I'm only looking for the 0. The time that, right, the steady state one, you just have to say, I'm looking for steady state. There's always dynamics for any amount of time that you want to look at. But if you just say steady state, that means you're not looking at any reactionary or impulsive types of dynamics. Or there's no oscillating sort of pressure gradient here driving any sort of flow. You could do that problem, though. Okay. Now, let's move along. So commonly right here, people, right, they assume purely radial flow. Right? So one thing in Jeffrey-Hamel flow, and this is maybe what I'm saying, is some people immediately from its steady state, the width is important, right? It's 2D, it's steady state, but they also have some symmetry thing, right? That these ones don't matter. Well, that's a purely radial flow. This I have problems with. Right? This means that, all right, it's purely radial being like, instead of like having a u of y, this is actually really like a u of r only. It makes it an ODE, essentially. So that's usually given to you right here. But then it's nice to sort of re-show these things and maybe see where the dependency came up on in a scale. Right? So you just kill this off. Or another really way they're saying this is sort of the same way as saying that Vz is equal to 0. This also could be said as like, well, purely radial. I'm just going to say that Jeffrey-Hamel flow is a purely radial flow. You can certainly everything is a lot easier if you start that way. But I want to maybe sort of use, let's say, the scales I'm defining to see when can I really say that. I would think for regardless of what dimensions I'm in. Okay, so if you want to get a handle on a velocity or determine some relationship of velocity, I have said multiple times, right? Continuity is used to solve for velocities. Don't forget that, right? If you're trying to figure out relationships amongst the internal velocities, that's what continuity is for. It's like working thing, right? Right, continuity is the thing that is helping you solve for velocity relations. So it should cue you or key you into something like this. You know, this one being 0 came from a scale, at least argument that I said that w is equal to 0. So I could get rid of that one just because that this is always going to hold as well. Throwing away the radial one isn't totally obvious, right? Because that normalization coordinate was what, right? So then you had sort of this star is n angle divided by the alpha. Well, alpha could be really kind of tiny or big, so it's not good, right? I mean, alpha is a bounded coordinate to begin with, right? It's only going to be from 0 to 2 pi or 0 to pi. So I have no argument there to say that this thing's just going to throw away in the derivative. Right, when I non-dimensionalize the theta, the alpha comes out. It's always bounded. That's the thing about radial flows, right? It's just going to be some radial value. W I could make infinite, so I could say that dies off. This one does not. So then how am I going to say that this is purely radial? Is there some scale thing that lets me know that it's purely radial? Well, if I'm trying to get a handle on velocities, use continuity. So let's use the continuity equation, right? So continuity. Right, this is just having the vz equals 0. So now solve for this. We don't really have to solve for it. Have a negative. Okay, so now you're maybe seeing this from homework 1 where you just start doing algebraic things like this, or assuming you do know what things are. Now let's get on to here. So this is this idea that now, okay, well I'm just going to say this is some velocity scale in the radial direction. And I want to have some idea of then what this one will be. So I call this one, did I call it V0 here? Yeah, a V0. Because this one's really sort of a Y. OK, so again, we're sort of assuming that we know these scales. And I'm just trying to see the relationship now between these two scales. OK, so then if I go to my scale world, what do I have? OK, I'll have put it all up there again, right? So here's continuity, inserting the scales now into these bad boys. Boom, boom, boom. Okay, right? So I've inserted these, and I've just made an insertion here, and then the L popped off, so then this goes away. Okay, and then it's not the most amazing conclusion, but you do see there is something going on here, right? Because of this right here, the scale and the angle did pop up. Okay, so now I do know some relationship that V0 in a scale sense is related to the radial flow velocity, but by this angle alpha. So it's non-dimensional, so I certainly can do that. It's just going to be a pi term. But this does say something now about this purely radial flow, right? Can you see it? The idea is alpha is, right, any alpha I mean, it doesn't quite make sense to have it be 2 pi, right? Certainly because it's a half angle. So you could just say, well, it's certainly bounded then before by, right, to pi. Problem with this Jeffrey-Hamel thing then with that is, okay, well now what solutions am I really modeling when alpha is like more than pi over 2? That's now the wedge has opened up, passed over itself, and I now get like an inverse wedge problem. So there's a lot of complications with that, and it certainly wouldn't seem that it would be purely radial then. So this does tell you, like, okay, well, I definitely do get purely radial flow if my alpha's small. Why? Because you're saying that, like, if alpha's pretty small, that means that right? A lot of values of angles really satisfy that, right? So this does get you there in the scale sense by using continuity for Jeffrey-Hamel flow. You really do see that this idea of purely radial Jeffrey-Hamel flow, you are kind of restrained, right? I mean, what are the odds of having a large angular flow that there's really no transport or there's no difference as I sweep around this way, right? That there's actually no velocity moving in the angular directions. What are the odds of that? I mean, the larger the angle is getting, right, the less and less these viscous forces from the walls or the vorticity generated in the walls can affect to balance out these differences in forces. So there certainly could be some sort of movement or flow happening between theirs. It would just be harder and harder to really get purely radial flow the larger your angle sweeps back out. So the scale is really telling you that, going like, well, I know you always really say that, but you know what? In the scale sense, it's only really valid to say it by dimensions if you do get a tiny angle. But again, you can plug these things in. I mean, the angles that satisfy something like that, that's, you know, it's not the end of the world. But certainly, but really the conclusion from that being, OK, I really do get purely radial flow if I have small angles. So sort of that's kind of, in a scale sense, I like kind of stop there and go like, OK, all these other stuff I see past this is a little bit iffy in my sense. Right? My opinion being that, like, when people are using Jeffrey-Hamel flows that are like are really viscous but really like wide, like I don't think it, you know, it's not really glued too much to reality, because even at steady state, some perturbation would certainly cause at least some radial flow happening, right, or some theta component of velocity. You just wouldn't only, right? So okay, so from continuity with small angles, now I've simplified it down even further, right, to this. Right, with small angle, or sort of just this. So there's my simplification of the velocity field again. These are always the most simplified versions of velocity fields, right? I've thrown away two components of the velocity field. So in the general solution for Navier-Stokes equations, with some arguments say like, didn't matter, I'm just looking for the one component in there. So that's usually, right, those are the easiest solutions that we have. So let's look up, right now let's look into more non-dimensionalization, right? So I only have this one to care about, the velocity in the radial direction, right? So this is saying I'm only trying to look at like something like that. Well, it's pretty bad, right? The idea is like any sort of angle I'm at, right? So whoop, it's just going to be some radial coordinate in there. So the velocity is only, there's no component of velocity here. That's what this is saying, right? You're saying that, like, if you threw that one away, that the vector is only comprised of this one. There is not even a little tiny, right? Any sort of swirl velocity you're saying doesn't exist in there as well. It doesn't really exist because of continuity and you have a small angle. Okay, so if looking for a scale for this radial one, right? Well, there's no slip on the wall. You got to imagine this going further and further down all the way down to 0. There's no slip right there. And that's this. OK, so what is this u naught I want to pick for the scale, right? So this would be a u naught. So we're kind of on the search for this. Okay. So back to continuity. Again, continuity helps you find scales for velocities, right? If I now insert this in the continuity, right, now I get this 1 over r. Dimensionally, I'm getting this right now. Right, because I've thrown away the angular one right there. And so much exactly the same way with all these pressure things where we said, OK, so if that derivative is equal to 0, that means the function is not a function of theta, right? So this statement right here, you can throw away this 1 over r, right? Also with radial flows too, you notice that too. In all these differential terms right here, if the r is allowed to go to 0, even these statements have issues as well. So you can even see these 1 over r's. This is this idea of not including the point. People do a lot of math, but to like, OK, so getting to the point right here. This is from continuity. OK, and what it's saying is that this is not a function of the theta coordinate. So right, that's this idea of these things being 0, or however you want to say it, but importantly, the conclusion being, I see. So that would mean that, no, not a function, not theta, not a function of r. So that would mean that this is only then some function of theta. Right, so you could think of this as this term looks like a constant with respect to the r. So that means that it's a function of theta, right? These types of statements you should just kind of hold in your head. Oh, that's what it's really saying. I mean, it's hard at first, right? But you can but you have to get used to them, especially in radial things, or especially anywhere. I mean, we did the same thing with like the slot pressure gradient flow. You said like, OK, well, if that's 0, then that means it can't be a function of x. Same stuff here. So that means that this interior of this derivative must be a function only of theta. Well, just dividing now by this. We did this also in the impinging flow. I'm just maybe doing it a little slower right now, because, again, I like this one. So now I have right, so by continuity, I at least have solved for the functional form of what the radial velocity must look like. It's got to look like this, some function of theta divided by r. Now that tells you what a good scale is, right? So that would mean, right, this function, if theta is 0, and then theta also corresponds to alpha, that's the sweeping part of this problem. OK? So as theta equals alpha, I have no slips. That means that this must be 0, not really a good scale. But then as theta is equal to 0, that's the maximum flow I could have, right? And that's this idea of symmetry, right? There's a symmetry argument here as well. But you really are just showing that, like, OK, as I move further and further away from the wall, I have less and less and less viscous forces, right, resisting my motion, right, because they have to obey no slip. So the furthest I can be away from the wall is exactly at 0. So that's certainly going to be your maximum scale you could have. So now I have a good radial velocity scale. It's this. OK. It's not, it doesn't seem too amazing, right? But importantly, right, you have just this function evaluated at 0. Okay, any function evaluated at 0, right? It's just a number. So just label this something else then, C0. But explicitly doing this conclusion, going from f to a theta, and then f going, what's a good scale? Well, here it's no slip, so that's going to be 0, but the maximum I could ever have is at 0. I'm just doing all these things for you, because even myself, I go through and reason these arguments to go like, what's really going on? OK, so now you have this C0, and now I can make a non-dimensional velocity. Right, so now we have our V star, which you really call a capital F, right? So if capital F to correspond to this, right? Little F. And what is it? We have to divide by these things, right? It's not too complicated. This is all it's not too complicated, right? This is VR, and divide by my U0. This is just all the F divided by a C0, because then your R's are going to cancel, actually. Important. So it's nothing too complicated or fancy right now. Maybe it is. Right? And then if I insert the non-dimensionalization of this, right, now I would have my completely non-dimensional, right, functions, right? So f, right, v star, really think of it as a capital F and an eta, okay? Where eta is equal to your theta divided by your alpha. Nothing crazy there. I mean, it's all crazy. Okay, so same process again, where now you're doing the thing where you go like, okay, I have my non-dimensional radial flow that I'm searching for. I'll plug it in with these etas and thetas, right? This is a natural, this is a natural non-dimensional angle because I'm just normalizing by the only angle coordinate I have in a Jeffrey-Hamel flow. And then this f of being a theta, right? That came from a continuity argument. So, and then capital F being the capital F being the non-dimensional version, and you just define it as some ratio. This C naught not being totally important until later. Okay, so that was just from momentum, right? So this has all been just from all we've used is just from continuity. I'm going to erase this flow right now as well, okay? Because I think at that point, hopefully, maybe someone wrote it down. If not, it's also written down in the notes, so let's move along. Okay, so that was just from continuity. So at this point, you can kind of think of, you can kind of really think of like, well, I've really tapped continuity out, I think. I can't really conclude anything more from it. So now move into using momentum. Okay, so we have those momentum equations. And now it's time to use them. Okay, so there's a bunch of terms in here, and just here's really how I like to do this, right? I keep everything in the symbolic notation, and then I just use my simplifications here. Like this one, what else does I have? What other simplifications do I have? There's like terms in here. Looks like that, where this is awaiting its positional argument. Okay, so this now I just redo everything in symbols and just do the dot products. Okay, this looks like this. Doing this multiplication out as well, I have a VR as a vector statement, and then I have this pressure gradient terms. They look like this. And other terms that pop up in the full equations, right, is I have this viscosity term. It's got a square right there. This comes down to boo. VR and over an R squared plus over an R squared. You notice I just hold my notes for this stuff because I can't memorize calculations anymore. Just do them once. Okay. But importantly, this is at least the process I do the calculations, right? I do them as I just define these operators, right? And then I just look at every term symbolically in Navier-Stokes and work on just simplifying that, right? So all these terms are used in the Navier-Stokes equations in like in the symbolic form I've given you them. So I do it this way, maybe to show you how I like to do these calculations if I'm doing them by hand or on Mathematica. I like to use as much continuity as I can to make a statement about like conservations of flows or relate velocities to one another and non-dimensionalize things. And then when I'm done with that, move on over to momentum and then do it this way, where continuity and scales let me define this operator in a better sense to let me get this 0 right here. And then continuities and continuity equations also let me say that this term is 0 as well. So now using the combinations of these two vector operators or tensors, now I just work out all these individual terms of the full Navier-Stokes equations. Okay, so there's no theta star dropping out because it pops up because the VR is what I'm trying to track. So now putting it all together, right? And I put all this together, and you get your momentum equations or systems. There's only going to be 2 equations in this problem, right? Because, again, we're saying that the VW is 0 because of that scale, or you're just claiming it's not. So then you get, right, I think I switched to U. Here's your system. Boo, boo, boo. UR, R squared plus 1 over R. UR, and here. R squared, do-ba-do. Putting out everything for this. Okay, and then the other one being this. Okay, right, so now these are just throwing all these terms together, right? I just added them up. I'm just throwing the terms together, right? So this one's equation 1, equation 2 of momentum, right? Or this one's being, right, this one is the radial, right? This is the radial momentum equation, and this is the swirl momentum equation. What is this one saying? It's similar to hydrostatic pressures and pressure gradients, right? But it's stuck around. So in order to try and get at a solution for right here, this is where you go to really a stream function behind the scenes, right? Remember, in a stream function, we cross-differentiate it to get rid of the pressure term. That's what's going to happen here, right? To get down to 2 equations, right, I just have a u of r, and then there's a theta here. Again, remember that a derivative with r is not, right, the derivative with the r, this thing doesn't go to 0, right? What we do, the only thing we know is that r times this u of r, right, looks like a function of theta. So if you see this, you don't go, right, you're not allowed to say that, because it's the multiplication of them that looks like this by continuity. So common mistake I think some people do is exactly that. Okay, so to eliminate pressure in this system of 2 equations, right, what can you do, right? Well, we're just going to do the exact thing you do with the stream function. So that could clue you in for how stream functions is also happening behind the scenes on this problem. Again, I'm just trying to get rid of this pressure term right there so that I could just calculate it later. Do you see I could calculate it later, right? If I figured out what u of r was, I could then, from the differential equation, I only have u of r in all of this stuff, right? So if I get rid of pressure and solve for u of r, I could then later figure out the pressure gradient by just plugging it back in, taking a theta derivative. Boom, I got my pressure gradient in that direction. Same thing. So keep that in your head of incompressible flows, as pressure can be solved for at a later time. So you look at this stuff a lot, right? And you just do this. You do this cross derivative thing, right? So for here, I'm going to multiply by an r and then take an r derivative. And then here, what I'm going to do, multiply the entire equation. I'm just going to take an entire equation and do a theta derivative, right? And in looking to get rid of the pressure term, what I'm really going to do, right, this is what I'm doing. I'm taking, OK, well, how about a d theta of equation 1, and I'll minus it by this. So this is really stream functions happening in the background, right? Right? And actually, Jeffrey-Hamel flow, what's amazing is if I tried to actually make the Jeffrey-Hamel flow a cone flow, right? This is a 2D type problem. If I were to actually do this in spherical coordinates and make it a cone flow, I would satisfy all the assumptions of using a stream function. So actually, in that situation, you could redo the exact same Jeffrey-Hamel flow again. You would just do it in terms of stream functions. Where you satisfied, it would then be looking for some stream function psi of r and theta. You plug that into the governing stream function, 4th order equation, and move right along. But it's nice to kind of see how all the systems work out. So this ends up being a rough calculation, right? Because now you have to take this derivative. It's a bunch of terms in there. You take this derivative with r. There's a 1 over r squared thing in there. So then that gets even worse. So I do it in the notes every step, so you can see how these things work out. But you end up that this thing will look like you are some product R, and then here's a cross. Now I have to do all these viscosity terms. Boom, there's a squared part there. More stuff. Here's boom. Minus 1 over R. A lot of cross terms happening. A lot of them. And then here, U over R. Okay, this is just doing this operation. Things cancel out, right? You get there are 2, so you minus 2s, you get 1s and negatives for operations, and everything ends up looking like this. Okay, so importantly, what's happening? Did I do this right? Right, sort of every term right here, you get this viscous, right? So everything with this new in front of you here, right? Here are then sort of these. Here are the viscous terms. How do you know they're viscous terms? Well, they have this nu in front of them here. And then over here you have these inertial terms. Right? So this problem is, again, a balance of viscous forces and inertial forces. So what should we expect to pop up? A Reynolds number, right? What is the Reynolds number? Reynolds number is a balance, right? It's a non-dimensional group scaling or telling you how important each of these terms are. So we should look for at least a Reynolds number somewhere happening in here. Okay. Again, this is also purely dimensional. I've done this one dimensional, right? But we have all of our scales. We have all these scales and all these non-dimensional things around. So let's not throw that away, right? So from this equation now, which has inertial terms and viscous terms, now I would plug in my scales for this problem. Now I would go like, okay, well now I want to non-dimensionalize that governing equation for the velocity in the r direction. So this u of r scales like a u naught. And what was the u naught? And then this eta is my non-dimensional angle. U naught was what? It's a c naught divided by an r. And then I also want to define then just sort of, you really would insert all the scales, right? And then you could divide by something. But maybe if you can't see it, I would like to just show you, right? You could have this u naught r over a nu, which is actually equal to this. I mean, these are just pure algebra substitutions right here. But notice, though, that just how this Reynolds number is right defined by here. You have really a velocity in the scale. Think of this actually, right? What is this term? This is an arc length, so that's really a good scale to think about, but then break it up in the angle. So this is a velocity times a length scale divided by kinematic viscosity. And then the c naught, just using the definition you have of that c naught. So this is what your Reynolds number ends up being. It's important that the Reynolds number has the angular coordinate in there as well, right? Because then that will show you the wider I get, the more inertial forces I have, the thinner the wedge is, the more it's dominated by these viscous forces. Think about all these vorticity equations or things we looked about. If the angle is getting very, very small, right, and the Reynolds number, right, so it would be dominated then by viscous forces. Well, if it gets very, very large, that means there's more room for a bunch of mass to not want to stop moving, so it should be dominated by inertial forces. So anything else I'm missing, right? So this UR is being scaled by this U naught, which is defined by that. And then what we have as well, so then we also have this definition of capital F as a function of eta, right? That's what we're looking for now. Right? In fact, really think of capital F, right, as really a non-dimensional, it's a non-dimensional version of this. I have that right? Yes? Yeah, so this is really a U of R. Supposedly all the terms in there, that's what you're looking for in searching for this F value. So plugging all these things in there and then dividing out by some term, you will then get, after all this said and done, these R's end up helping you You get the Jeffrey-Hamel governing equation. So you take a breath, take a little break after this point because it seems like a lot of work and arguments I've been doing just to simplify down all the statements of Navier-Stokes equations. But after some massaging of math, right, you do come up with a simpler ODE that describes the flow field. If I can figure out what capital F is, I can figure out what the radial velocity is, and I can figure out what the theta part is. Right, so this is good, right? This is the governing. Okay, that's it. What have I said multiple times? This technically is the solution, right? You have defined the function of velocity, right? Your goal, you set out in the Navier-Stokes equations to characterize the velocity field. Through scaling and continuity, you show that the velocity field really only has one component, and that being radial, if some assumptions hold. So that means to understand the velocity field, you must understand what the radial velocity component looks like. Non-dimensionally, we're done, right? We have a definition, right? The radial velocity component is the function that solves this differential equation. Solving it is a different story, but that's why I think you should take a break and pause and celebrate if you do this step ever. Determining the governing differential equation is usually the end of analysis these days in fluids papers. They write down the governing equation based on some assumptions, go like, got it, and then numerics, and throw it in, got it, boop, boop. Because that's it, right? However anyone wants to analyze the solution of that differential equation or what it looks like, that's up to them. What I like about Jeffrey-Hamel flow, though, is that all the methods are hidden in it. But with all these things, now as the person thinking, right, it's not done after you just get this. You have to assign boundary conditions or initial conditions. So as a boundary value problem, what do you have? Well, at the center line, that's given for free, right? The center line is my maximum flow rate, which I non-dimensionalize by, so I get the 1 right there. And then what else do we have? Well, we have no slip. How about this? Okay. These are no slip, where, right, because the angle could go down or it could go up, the idea if I'm all the way at alpha, I must have 0 slip of the walls. If I have all the way down at alpha, I have no slip of the walls. What is no slip? No slip is the double slit experiment of fluids, right? You always can write that down because the fluid must obey it. It doesn't make this easier, though, this problem. So the second one you can have is you can, instead of these, so this is sort of option 1, the other one you have is to then think about the symmetry happening in this flow. So symmetry boundary conditions are posed like what? Symmetry is that a derivative at the 0, right? That's a critical point. So this one's always holding. That's what you non-dimensionalize by. And then the other one, what do I have? And then at the other endpoint, you again have no slip. So this is option 2. And these are symmetry boundary conditions. Right? The symmetry boundary condition being that the derivative at the 0 point has my maximum, right, is a critical point. So this is almost inferred because this means that, right, this means that there is a critical point there, or there's a minimum shear value right there. So you also think about the symmetry condition right there. Minimum shear, right, and that's also imposed by you assuming that the maximum velocity is there. You're saying really a critical point is happening at the center line. There's also more, right? In fact, there's a much more impressive set of boundary conditions. There's also this issue of the flow rate. So the other one you have at your leisure, right, is this idea dimensionally, right? This is maybe hard. This maybe hasn't been seen before. But this is a flow rate or an integral condition, right? An integration, the mass flow rate condition. The flow rate in is equal to this. So if you know flow rate, then that's how you're restricting this, right? Pretty cool. All these boundary conditions are just this ends up being the simplest analysis, though. All these things actually infer one another. Is what's amazing. It's kind of fun to play around things. But the symmetry one, I think, is the symmetry one is the most bang for your buck. But you're still assuming. I mean, you're really, what's your assumption here is that there's a critical point at the center line. So there's like you've already said that the maximum shear happens at the 0 line. So this one's fine from that. This 1 to -1 with just using no slip conditions, and then this normalization time right here, you get the same things, it's just a bit harder. And then this one's even a little more intense, just because it's now a integral condition to the to the boundary value problem. Okay, so one way I think this is we can also non-dimensionalize this, right? So then if I have my d theta star, let's say, no, d eta. What was the eta? So the eta is there. So then alpha comes out. And there's an r. VR. What was this? U of r. On my scale here. Is it RDR? No, RDR. RD theta. And the radius. So my radial scale is going to be what? I scale like that. Everything in here. Did I get this one? So oh wait, I also know that. No, this was important, right? This was equal to a function of theta. Okay, sorry. That's equal to a function of theta. So non-dimensionally. And then this is an area. Where this Q is now a flow rate per unit width in and out of the board. Okay. I'm missing something in there. There's no Reynolds that popped up in there. I think so. So this is just this condition right here, that you have this change. So if you assign this then then these things also follow from here. Okay, now let's get along to here. I didn't focus on the integral boundary condition as well in these notes. I didn't want to throw that on you as well. Okay, so now there's three things to do from here right now. So option, right? So that you assign the boundary conditions. You could do numerical analysis, where you solve the equation just using your computer, assigning these things like you did in homework 1. You could use totally analytical stuff. We can just keep mathing at it and see if we get anywhere. That's just that's closed form analytical methods. And then there's even approximation methods, which are asymptotics, right? So there's sort of three options, right? We could go numerical. Okay, so approximate solution being, right, I say approximate because we all know that a numerical solution is still an approximate solution, right? But I have a specific meaning of its approximate solution because of this term R, right? These terms, these parameters that pop up in there. So this one's neat, right? This is the theory really of asymptotics. Solutions, right? This one here is a theory, right, of really Jacobi elliptic integrals, right? And this one here is just sort of like the theory of I don't know, being at work and just lazy. Sorry, it seems like I hate numeric stuff, right? But so like, what is like, so this first option you have is really sort of just like, I really do sort of just see this stuff really as just sort of like basic investigation. Right, sort of searching through the forest of math with a little tiny flashlight. That's all option 1 is. Always. Okay, then the fully analytical one and this one kind of break. You'll see that they kind of like break areas right here. Because while you can look at the analytical stuff, right, and you have these Jacobi elliptical integrals or whatever. I don't even go into the right. This more so is really telling you, right. This is sort of this analysis sort of like sets limits. Right? So you might not be able to know what the actual solution like really looks like, but this analytical stuff, what you get is like you can really see the stability or limits on the equation purely based on this Reynolds and alpha, instead of just seeing that the solution failed when you tried to run it. That's what this stuff gets at. And then these approximate solutions or asymptotic methods, what they are really telling you right then, sort of the actual initial boundary conditions. Okay, so the approximate solutions, what they tell you is they really sort of show you, right, how the effects of this Reynolds number and this alpha are playing into if I wanted to actually make the plot of velocity as a function of theta. The ellipticals ones claim they do as well, and they're like a totally analytical solution. But I really want, I stop right after I get to the integral itself, the implicit integral, right? Because then after that point, Jacobi and people like that just said like, aha, so that function is a thing that they defined it as a thing that solved this implicit integral thing, and then went along with properties on that. But it's really over after you write down that integral, I think. You know, even if you code up these three Jacobi integral functions, people then just had to come up with methods on how the heck to calculate it anyway, based on these approximate asymptotic methods. Okay, so So maybe I want to sort of lay that out of, there is a limit, right, of how this stuff works. So without further ado, then, let's get at it then. Let's actually go at this mathing it out more. Let's just say you have a true belief that, like, well, I know it's a nonlinear ODE, right? So you could just throw your hands up and say there's no solution to this at all. I have no luck. But, right, why don't you just try it? And so this one, we're not doing that. It's lame. Right now we're going to do this side right here. Okay, so you're looking at this differential equation. What do you have? You don't have much of it right now, but whenever you do see a term like this, maybe you haven't done this before, right? And there's even something else going on behind the scenes. This sort of thing, you should always sort of immediately go like, aha, I can turn that into like this derivative right here. Right? It's just you're just undoing a product rule when you put this half right there. Right? It even gets rid of this 2. So maybe you haven't seen that before, but if you stared at it long enough, or if you did calculus enough in your lifetime, you certainly would go like, I can do that here. The benefit of doing that is what? Well, the benefit of doing that is you see there's a derivative here. You could turn that into a derivative, and you could turn that into a derivative, right? So, right, the idea of rewriting that middle term, then you can make it look like your entire differential equation to look like this. Double derivative okay? All I've done is I just said, aha! Right, the f and the f prime, I'll rewrite that in terms of derivative, being that you can then write that this equation with the derivative must be equal to 0. I've just rewritten something here. And then the same thing we did for the theta, right? When you see these types of expressions, right, you go like, OK, well, then that means that this must be a constant value, right? Because f isn't a function of any other term but eta. That's how we defined it. So there's no like other function hanging out on the other side. That means that this must be only equal to a constant value. Could be 0, could not be 0, doesn't matter. But you can then make that claim. Importantly, what you've done is you've dropped the order of the differential equation. Third order is always going to be harder than second order. So if you can drop the highest order in your differential equation, you're certainly getting somewhere. Okay, so just fancy little substitution, right? And then you just come to this. I think I wrote a k. I'll try to keep that. Did you get that? Hopefully you understand that idea when you're doing these types of differential equations. Okay. What's really happening though as well is you also could just integrate the whole differential equation, right? I'll just integrate this, right? And then what you're doing here is you're then going to do integration by parts on this term right here. Integrating this just gets rid of one derivative, right? Then linearly move it over to here, and now you have this integration by a product of two functions, where one's a derivative, one's not a derivative. So then you would integrate this term by parts. Then you have a boundary term and then an integral term, right? Then this thing right here, it's just a derivative, so it just goes away as well. So you could just integrate the differential equation that's nonlinear, right? And the idea is what you've done at this point is you have now an integration by parts. Fun exercise to do, right? Or extra credit. If you remember what integration by parts is, right? So what did I tell you about calculus, right? The grab bag of math tricks is no product rule, no chain rule, no integration by parts, and no use substitution. So you wouldn't even have to do a fancy substitution here. You would just then go like, OK, I'll integrate my whole differential equation. And then you go like, OK, I have an integration of products of two functions. I move a derivative over for integration by parts. There's the f squared comes from. OK. So seemingly almost things like we're done. And then there's this, now there's this worst part where you have to arbitrarily then multiply by another, where you have to multiply by a function to kind of get the same trick to happen again. right? So now what you do is you then multiply this whole equation by the f prime. Why would you do that? Well, you're kind of, well, the same way that it worked here, right? I can get the same thing to work here, right? Because I have a derivative and then the second order derivative on the other side of it. So you can kind of go like, well, I could actually probably get the same thing to work, at least on this term right here, right? Because what do you have this? This is again the same thing as this now. Right? It's just this, just the thing is now, this thing is now a derivative itself. So I can get rid of that one there. Okay? And now I'll have this f prime f squared. Well, that would be, yes, that is a 1/3 so sort of just like how this is a half, right? If I just have one derivative and then just a bunch else, right, I could just, right, always maybe invoke this, and then again here. Right, so if I multiply the whole thing through by the equation, then I get here, I get this total derivative expression going on. Where now I have, again, a d eta on every single term in the equation. It doesn't say red, by the way. This isn't a Reynolds number times the alpha. OK, so all those substitutions go into here. Essentially, I multiplied by an f prime, and now I get this expression here. Squared, a minus, a minus, okay. Doesn't seem like I've done much. So now, what do you have? So we just did 2 rounds of just the classic nonlinear tricks to, if you have a nonlinear ODE, try to make it look like an exact expression, meaning you just have this, where you have a bunch of stuff on the inside of parentheses multiplied with a derivative. All right. And again, what is the goal of this? Is now this expression this is first order. So you did 2 rounds of math because in each step you were dropping the order of the differential equation. And that's really all you have to do in almost any differential analysis of trying to get at some sort of solution. So I never really did any solutions for you right here. Again, I told you multiple times, this is my favorite solution, so I like to look at like every aspect of it. So really, I remind myself how to solve differential equations by just going over Jeffrey-Hamel flow again, because even the methods you use in this are also being used if you solve a linear ODE by hand, if you want to do it that way. But there's certainly need. I mean, this like it is sort of like, right, we're lucky that it does work out this way, that we can just get all the way down to a first order by some algebra. Certainly are. But you can be inspired by just the methods of what you're doing to get there in the first place. See if I'm recording. I was like paranoid and I forgot recording. Okay, so right, the whole point was doing things to drop the order of the equation. That was it. So now what you do here is you integrate this expression now. Right, so now I have this shorthand here. What does this mean? This is the terms, you separate them on the boundary, right? The derivative with respect to eta of a derivative of eta is just equal to whatever is inside the integral, right, evaluated on the endpoints or the boundary points. So this being an arbitrary eta, and then you relate everything now back to some f at 0. Again, stream functions hiding behind the scenes right now. Again, right? Remember when we did the asymptotic suction flow going through a plate, we had this bounded term right there, right? We had this reference point of psi of 0, 0. It's still hiding beneath the surface of what we're doing. Okay, so this is where boundary conditions come into play, right? Because it's nice to use the symmetry condition here because of this. That's where that's the nice part. Okay. So in the effort of time, there is a algebraic manipulation trick here that is nice to get it into a nice working form. So again, with my pretty math stuff, reference to this sheet of notes I have for all of the steps, I think, because I don't want to do it right now. Because I just rather get to, okay, well, you do this, and now you have this new expression just of f of etas, and then it's zeros. Importantly, you use that the f prime at 0 is equal to 0, and you use then, well, I know what f right at 0 is as well, right? The ones I use, yeah. So I have f primes and f, so then f of 0 is equal to 1, right? So I know what f and then f prime are at 0. That's where the symmetry condition really helps you in this analysis, where if I'm using the symmetry boundary conditions. Right, so f0, that's the 1. And then you just use all these things when you do this integral, because now I have the f at eta, and I'm subtracting off all these f's, but evaluate at 0, and then things drop out, or things turn into 1, and then you rework things to make them look like this. Okay, this is sort of it. And then just, well, it doesn't really actually matter what that's his, but there's sort of just a bunch of constants lumped into here. That's the important point about it here. So this C actually has this K and all these other things that are coming up around there. This C even has a Reynolds and an alpha in there as well, right? So it's better maybe to think of this actually as, well, this is a function of the Reynolds, the alpha, and even this K expression, right? This K is right here. Yes. So this is right. The idea that there's a bunch of stuff in there that you can see explicitly if you look at every step of the calculation, but it doesn't really matter because it's just like a bunch of constants. You just put it on the other edge right here. But importantly, factoring out this 1 minus f does something nice for you. Okay, so here this is the point of getting things down to first order equations. If you can get the order down of a differential equation down to 1, there's hope of you then being able to integrate the equation to then get what the relationship is. What I mean by that is now I can take the square root, separate, and integrate, and I can get an expression implicitly then for this. Is it 1? Yes, I have f on the bottom. 1. Then I have a df. Boom. C. Okay. And this is, right, and this is somewhere. This certainly is somewhere. It's an implicit solution. But a solution nonetheless. And there's a bunch of stuff going on here, right? Certainly, now there's a bunch of issues now with that constant c, the fact that I have something under a square root in the bottom. And then from this expression as well, right, you also can satisfy the boundary conditions. So this implicit equation also comes with the implicit solution, And how do you solve now for this C value? Well, this C value is solved for, right, applying the boundary condition, right? So when eta is equal to 1, no, when eta is equal to 0, this. When f is equal to 0, eta is equal to 1. You know what, I'll just... Okay, so all that really changed here is this, right, the bound on the integral, right, the bounds on the integration, right? Do you see that I have this being like an f of eta here in the bottom? So applying a boundary condition to this implicit equation says what? Well, f at 1, so that means this is 1. This would be f at 1. F at 1 by no slip is 0, so now I have my 0 to 1 integral. And then here is just going to stay the same. So you solve then for this C value with this. This solves for C, right? Even though f is what the function we're looking for is, right? This is now just an integral, right? With respect to just, this is just an integral now with respect to just like f being your x value that you have, right? And the idea is if you have a, I'll just write the thing out, right? So now you could make now numerical plots that are better than a numerical solution because now I have direct dependencies. I have a much more educated guess of what to really solve for in terms of my alphas and my So the C now, I have now this C, this integration constant now I have to find implicitly. And what I mean, I mean now that you could, now you can numerically integrate this expression right here at a value of R Reynolds and a value of an alpha, right? And they'll vary the C in this numerical integration, right? And then be able to solve for what C is. Okay, so while now you're still kind of going back to numerical methods, right? They're not just lame numerical methods where you just write out the equation and start asking the silicon god what is going on in this world. Now you're doing a much more informed analysis based on the integration here. Now what I'm saying is I want to see this dependence of what this C is, right, for any sort of R and alpha. Right? You don't get any of this if you just solve the differential equation with some Runcutta scheme or something like that. But this is having far more implications of what this C value is. I mean, what this actual thing is important as well. There's even more things just about this expression that help you do. I look at this thing tons, and I don't go from the elliptical integrations here. I mean by elliptic integrals. So that's also sort of the idea of where this kind of leads into elliptic integrals, right? The whole thing is when you write this down, you have this square root of this polynomial on the bottom. And then Jacobi elliptic integrals, they're defined in the sense that they are the inverse functions that solve things like this. So it's not the most satisfying solution, I say, when you get there. Because it's sort of and they only got there because back in Jacobi's days, right, they dealt with these types of implicit solutions of differential equations so much. They just said, well, screw it. I'll just call that a function and then think about it later in terms of series. So that's kind of the history of, I guess, where they come from. Okay, and then the other cool thing is if by factoring out this 1 over f, the algebra in there, right, there's this 1 f, right, and this thing, right, really is not 0. And it's not 0 because this integrand is only happening on 0 to 1, not including the value. Right? So you assign, the only time that f is actually equal to 1 is when f is happening on 0, right? So this is the idea of assigning a boundary condition, right? Is the differential equation occurs on the interior of the domain, but you set the function value at the on the domain boundary itself. So by factoring this thing out, I can still play with the inside and be in a safe space where I know that this isn't going to drop to 0 ever. Should I keep going? Again, I like thinking about this thing ever. Again, it seems we're so far removed from anything, but right at this stage, I'm maybe just showing you like how deep you can go to any solution, right? It amazes me. I haven't even drawn exactly out even a velocity profile yet because in this analytical world, you can't really do it. What can we get? But from here, though, I would say there's a neat sort of something neat comes down when you do make this plot. This is the C situation here. Right? And sort of to get away from an alpha situation as well. So this is going to be a positive Reynolds, and this is going to be the negative. Does anyone remember this Reynolds thing? The issue with it is the Reynolds right now has a direction where this flow can work as an outflow or an inflow, and that being defined by the direction. So the Reynolds number itself has a direction associated to it because the flow of the Reynolds could be an outflow or inflow. The outflow being leaving the Hamel's wedge, inflow being going towards the sink point. But kind of neat, when you make this sort of plot for a small alpha, it kind of ends up looking like here. And then this point being when fascinating. All coming from just all of it coming from just solving this boundary condition problem over and over again. Now, people vary alpha a lot in this thing, right? People vary alpha quite a bit, but I think I like just having that alpha, right, this being much less than 1. So this graph, right, for instance, is when alpha is really small, a small number, right? You can numerically do it for anything, but this is now a pretty neat, right? This is now some neat importance right here, right? Where if I have outflow, if I now have the positive outflow scenario, there's a limit now, right? There's a limit to when the solutions are existing. Okay. It doesn't, right? And the thing is, like, it doesn't actually even go to 0 past this point. It just disappears. So depending on the Reynolds and the alphas that you set, right, there's just some endpoint. If I'm going less, right, if I start going negative in Reynolds, this C's always exists, so then I always have a solution for the system. But you see now there's just this limit now for, right, that you have of the combination of the alpha and the Reynolds coming from that coming from that integral term. It's really even coming from this quadratic term right here that you just analyze and look at it. You just Desmos it. And it ends up being 10.31, right? For positive outflow. For negative, though, for the negative flow, there's no issues happening in there analytically from this thing happening right there. So in the inflow case for Jeffrey-Hamel flow, it seems there's no problems at all happening. But then in the outflow case, I now have some limit such that like everything broke down. Now that makes now let's kind of now jumping back. This does make sense though, right? Because in the Jeffrey-Hamel flow, right, if I think about outflow happening, okay, this is what I was looking at, right? So now if I think about outflow, okay, maybe it's going to certainly look like something like this. I haven't drawn out the velocity profiles quite yet, okay? right? Eventually for the outflow, right, if it's just blowing up too much, right, this could be like really, really slowly, right? But if I'm just, right, if the Reynolds number gets really large and it's blowing out, right, now if it's blowing out, right, essentially you might have something work out pretty well right here, but then you'll have some like crazy like jetting that will start to occur, right? So here's just sort of a wake that's occurring. Right? If my outflow velocity is too big, then I have no solution to all the assumptions of the problem right now. What really broke down? What broke down is now there's a bunch of swirl velocity happening, right? Right? So this idea now of this alpha being too large in combination with the Reynolds is showing you in your outflow thing, right? It's either the issue of your angle being too big or the Reynolds being too big. Now, for any set angle I set right here, regardless of my assumptions actually on how it is, say it's even a really small number, this means that there is just a speed I can go such that I'm just going to start creating swirl velocities and some wakes happening right here. It makes sense, right? If you just have a bunch of dust in this jet right there and you start jamming fluid through that thing, it's not going to be smooth velocity profiles that like are obeying no slip of the wall. It's just going to be an enormous amount of turbulent wake going on there because there's just too much mixing. You're dumping too much energy in there to just exist in one dimension, right? Navier-Stokes essentially is saying, I got to distribute that energy into the other dimensions of this flow right now. I can't withhold it in just this one here. And then just having this 10.3, it's neat, right? But you already knew this was going to happen. But this 10.3 being, if you are going to have outflow in this situation, if you do need to have your model of a Jeffrey-Hamel wedge type flow, and you do need to be having outflow, just make sure that, right, you're really far below this, right? Now, again, what does this also say? This is going to happen regardless. Even if I have a small velocity, well, the Reynolds number, if I zoom out further and further and further, right, the Reynolds is going to grow still because of the length scale growing along with it. And we still are going to expect that with this outflow Jeffrey-Hamel flow, right? As I spew fluid out from here, maybe around here, even if I'm going at an extremely low amount, right? Even if I'm going at an extremely slow scale, right? Even if I am going at a really, really slow speed, right, in the Jeffrey-Hamel, but I'm going outward, maybe it could look like this, and then it looks like this, and then it's starting to look like this, and we're having issues right now, and now it's like blowing up, and then woo, 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 and now it's, right, now I just get, right, this converging wedge thing is happening right now, that as I'm growing further and further out in the angle, I'm still going to generate those things. I'm just going to do it at a much later time. Again, this can still be from a very small angle and slow velocity. It'll just happen a lot longer. Now, this plot does say, though, it seems, though, as I go further and further in the negative direction, so if I have in Jeffrey-Hamel flow completely in flow, so now I have some amount of flow going in, all coming down to like an imaginary point right here. This is problematic as well because, again, remember we had the infinite velocity, which wouldn't happen. But much like a vortex, which is going to have to happen right here, is the wall. It's going to get so close to the walls that the fluid itself, viscous forces, will damp anything out, right? And if it's really, really small, you might even have like heat generation in there from just all the fluid moving so fast. So now if I have some situation going on like this, right, if it's kind of slow, right, you're just going to have like this, right? Maybe you just have these parabolic sort of looking type flows going in, okay? And they're converging, so however much, the thing is the converging duct is at least accelerating the flow, so it's always balanced as it's going towards the center of this flow now. Again, this is all just coming from me trying to reason right now, this idea that from this implicit solution of Jeffrey-Hamel flow, there's no issue in the negative coordinate when it comes to finding this constant c, right? I didn't do it here, but again, I think I almost got 3 pads of paper of me just redoing Jeffrey-Hamel flow. And I have some notes where I just go like, why is this happening? You actually can just look at the discriminant now of this You just do an analysis of the form of this. Oh, it's so cool. This is so cool. Okay, so if it's really, really fast now, really, really negative, or extremely quick flow jamming towards into the Jeffrey-Hamel thing, well, what's it going to look like? Well, it's just really going to look like this, right? Now it's just kind of looking like plug flow, in and in and in, right? Right? If it's very, very fast flow, there's mostly inertia flow happening. It just looks like some, right, all that's happening is some constant flow going inward, and all of the effects of the boundary layer, right, that's that right here from this Jeffrey-Hamel flow. If it's going extremely fast but towards the center right here, I don't have a problem really with any. I don't have a problem with any wakes coming or backflow occurring, right? I don't have an issue of backflow occurring because as I converge in the duct, it must be getting faster. So there's no point such that you would have backflow occurring, right? Right, the backflow can occur because that would mean that you would have some region here where it's getting smaller and where the velocity profile must be getting smaller, so then some velocity has to be going outward that way. But that's not going to happen because conservation of mass, right? As I go further down here, it all has to accelerate more, so there's never a chance that the velocity vector is going to start going the other way, as opposed to the outflow condition where that has to happen because it's diverging. But again, you're just kind of seeing this play out right now in just determining determining that I can always figure out this integration constant given any Reynolds and alpha. But all this is just me sort of just rationalizing some elliptic integral expression under an integral sign. And that's what fluid analysts do. They study the equations of motion for the velocity profile. They look at the terms in the equations. They look at how the parameter dependence changes on solutions. And then they internalize that and try to say it in words. OK, so here's a summary of everything you really learn. Right? Here's a summary of everything you really learn about this under the root radical by numerically integrating it. Right? And this is everything you really learn from a parameter sweep of the alpha and the Reynolds. Right? Okay, so we have this is a stupid one, I think. But of course it would look up. Right, so this is saying you learn from this parameter, right? You can never satisfy this boundary condition, right, at any way, if you have the angle larger than pi over 2 or between pi. Now, what is that saying? That's that means that like you're just in your office and you're just tinkering around. You're being really stupid right now. That's stupid. I think so. I mean, right? So now that means that this angle is greater than pi over 2. So now you've turned your wedge flow just completely not even to the picture that you drew in the first place. Right? I mean, certainly maybe you think it should, like, maybe it would hold, but no, right? So this should check out, right? Okay, like think about that even still, right? So here's the point, right? And this idea that there's no solutions for a wedge that looks like this with an infinite point source here. Now, if the Reynolds number is positive, that means I have outflow. Okay, if I'm further than here, that means as soon as velocity moves out of this thing, there's going to be swirl, right? There has to be some amount of swirl happening. Because if I have no slip here, right, at the very points of the edges now, all of a sudden I do have velocity outside the point, I am immediately creating a vorticity right there. So that means that there has to be swirl, and that would imply, right, that means that can't be 0 then. So certainly this should hold. Second thing you learn, just again from trying to solve that equation right there. Some solutions. So I just write them all down. Okay, what time am I at? I'm probably going way over in Jeffrey-Hamel. 1:46. Okay, for here, now I have alpha. So now we get into the situation where we're like, okay, that makes sense. So this summarizes everything, right? And there's just some more esoteric cases, really, of this idea of having your angle being like this. So for number 2, now again, you have this. You're not even drawing the picture of what you set out to model. So why on earth should something work like there? But you learned that like something kind of works. So now in this scenario, where the Reynolds number is negative, now I need to have flow going in. Okay. So now in these situations, right, it looks like this, but this will kind of work, and it ends up being if it's really small, so a very, very small region of space, right? So there's just some works right here where now it's kind of like here are contours of velocity. I don't quite even actually believe these things, though. Problem with this one being, if this is true, and now this Reynolds negative, you like need to actually have an infinite velocity at this point right here. So maybe it's something. Here are the important ones, though. For the alpha less than pi over 2, right? Now you're actually drawing the corner that you do care about, right? This is what you set out to really. Okay, here's where alpha is less than 2. And now we just have this graph right here and what's showing us, right? It's saying, right, when alpha is less than pi over 2 and my Reynolds number is negative, I always have a solution. This graph is always outputting a unique C value, so there's always a solution. Now the issue being, right, when Reynolds is positive, I bottom out. Small range of solutions, right? Unrestricted domain of validity. All from this graph, all have come from numerically solving it. Now, you can do this. You can make conclusions without having to numerically solve it, right? And they come from me just playing around actually with this quadratic form right here, right? So the issue here being, if I want to actually solve for that 1 and for this eta bear being a real number, remember that the implicit solution itself is eta f, right? Here's the implicit solution. For this C, you're really just solving for the, right, you're really solving for that boundary condition. But right here, right, that's where you have to solve for. But you also just, so 1 right here, and then you have a 0 right there. So a lot of these statements actually can kind of get out. You can't really calculate explicitly the 10.31. I couldn't find a way to do it. Maybe it's out there, but I kind of want to have it be like a self-challenge for me to like get it on my own. Because it's an old problem. People study it so much. But like again, all the methods are in this one problem. So you can just keep looking at it over and over again. So with this one, you can just look at the discriminant, right? You can just plot this, right? What you can do is you can plot this polynomial in Desmos and C when it's becoming negative, when it becomes 0, right? So certainly you can never have this, right? You don't want this to ever be equal to 0. So that's one analysis you get, and that's where all these issues where you have no solutions popping up. Okay? You will have no solutions popping up if this polynomial on the inside of here becomes 0. Again, you fix this thing never being equal to 0 because you've defined it, right? The differential equation only happens on the interior of the domain. You're safe there. There is where you can play around with parameters, right? Because this is a quadratic function. I have the quadratic formula, blah, 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 blah. OK, I need to move on. I've got way too much. But again, you can just keep digging into this integral, and then you can have these relationships about Reynolds number and the alpha and limits of when solutions exist. All right? But let's have a little more explicit thing, because now all of this has been saying, all right, I was just kind of drawing these velocity profiles, right? But if you want to actually draw a velocity profile, you'll have to solve for the f of eta. You will have to actually, right? You will have to actually write it down, and that will help you draw the plot. So hopefully you appreciated then this this just me going on and on and on about just this analytical thing where I implicitly solved a nonlinear differential equation, and I just looked at this term in an integrand, right? You can numerically look at that term. I didn't do the actual like analyzing the whole situation. Okay, so now let's do this approximate models, right? Approximate solutions, right? So now we're going to make assumptions, right? Okay, now we're going to say Reynolds numbers small or big. So our solutions will not talk about alpha. I like the way I think about this is like, well, I think alpha should always be small, right? We already went over this. I think for my scale arguments in this Jeffrey-Hamel flow, alpha has to be small because that's how you really can guarantee that no swirl velocity thing from continuity. So differently, how I think about Jeffrey-Hamel flow, I think like it's a combination of alpha and Reynolds. Like I like to think of it as like, well, the alpha has to be at least a tiny number, right? It can't. Certainly not past that pi over 2 garbage. Okay, so where was the differential equation, right? So, look back. We wrote down a differential equation, right? So now we'll go approximate on this bad boy. 2 alpha 4. Okay, so that's the nonlinear thing we're attacking right now. Okay. So let's look then, right? The idea is, what does it look like, right? What does this differential equation look like when the Reynolds number is going very, very small? Okay, and I mean going to small, right? So that means there's actually a point when Reynolds number is 0. Okay, so then at 0, I have a differential equation that certainly is easier. Think about it as when the Reynolds number is 0, I get rid of my nonlinear term. Great news on that. So in this idea you have, well, if Reynolds number is actually 0, the problem looks like this. Okay, that's then your governing differential equation system when Reynolds number is 0. Now, is Reynolds number ever 0? No, that's garbage, right? If it's actually 0, that means there's no flow going on there, and you should stop doing analysis. Okay, so it's more important to actually kind of maybe see what's happening like on the other side of this. So this is where some sort of asymptotic thing is. So this is then the ansatz you make, right? You go, well, what does right? So I'm going to say that this looks like some easy problem, right? Plus some correction term based on the small Reynolds number. Okay, this is an ansatz. Ansatz meaning you're just assuming some form. Right? Has many other names. It's called a naive expansion. There's a bunch of things, and then there's more theory going into what you're making this expansion into. Okay, in reality, this idea that you're saying that the function of f is asymptotic to some number of functions times the Reynolds number. Okay. Okay, where my Reynolds number is some small parameter. Okay, so this is sort of where less than 1. In fact, really just when Reynolds number is less than 1, this can be said, right? Because Reynolds number is less than 1. Right, when Reynolds number is less than 1, this r to the k is getting smaller and smaller and smaller, so that these functions at least are converging, maybe are converging to something. You don't actually know because you have to solve for what the f of k function is. And we'll do that. But the power of asymptotics, right, is the idea that any series that looks like this, right, any sort of, right, I could always write out this summation. You know it's asymptotic to something. And that's proved by like the implicit function theorem, and there's a lot of great defense on like this idea of you just saying it's right asymptotic to anything. I could maybe do that in the math lecture of maybe justifying this stuff. But it doesn't really matter. More importantly, right, this is the idea. You say, well, there's the zeroth order term, right? There's this easy problem right here. And then you want to find out how does Reynolds really affect this very small solution, right? So the zeroth order, right? So the zeroth order solutions right here where there's really no dependence of Reynolds in there at all. But you should have some dependence of Reynolds to really talk about or vary the flow rate, right? Or how you can vary that speed and put that in the solution. That's going to come from here. where you just say that the Reynolds linearly scales up some other velocity profile. Mathematically, you're just making this ansatz. That's it. So you kind of just start there. All you do. That's the idea. For an approximate solution, you have to just make this assumption that, well, there's an easy problem, right? When Reynolds is actually 0, I can solve the problem. And then you just make this little perturbation, right? There's a difference between perturbations and asymptotic series, but don't worry about that. So, but in the first round of maybe you never seeing this stuff before, I think just do this. Just make that ansatz, plug it into your nonlinear ODE, and see what's going on. Just do it, right? And see, right? Shut up and calculate what people say. So what ends up happening then is you then have to match up all the terms with the Reynolds in there. Okay? So what is, right? This is just going to be F0 plus my Reynolds number. Boom. Right? And this is just the linear distribution of a derivative. What else do we have? Okay? So now an F prime, right? This multiplication now this multiplication is that, and then the other one there, the other term in this expression is just again by the distribution of the derivative, looks like this. Okay, notice there's a subscript 1, subscript 0, subscript 1. Subscript 0 is a 0th order equation. It should always be very easy to solve. It is easy to solve just because you notice that the Reynolds number is 0. I remove the nonlinearity. Okay, so you FOIL this thing out. It's not that bad. So boom, 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 plus R. Again, I mean, I don't. Sometimes do it by hand. Maybe if you're on a bus, do it by hand. But really, you can do it by hand a lot, actually. You certainly get quicker at doing this. So there's a thing right happening here where this is now Reynolds squared, right? So if Reynolds was a small number, this certainly is even a smaller number. So this term really just looks like this. But maybe you can kind of see just the algebra of like separating these things out. Okay, what happens is you have a bunch of terms that have Reynolds in them and a bunch of terms that don't have Reynolds in them. Okay, so then just subbing everything back into a differential equation, now it looks like this. Reynolds now here. Got there. Now I have an F1 from there. I have a 4. F prime. Okay. And then I have this here, because that's this expression right here, but I multiply through the entire thing by a Reynolds number, so I just keep here. So then this is then 2 alpha, yes. Okay, so notice when you sub this nonlinear term right in there, right, because I've multiplied through by a Reynolds, I only take the very leading order term right there because that has a Reynolds in there as well. And then right, you can keep doing this, and you'll see that there are then, right, these terms of Reynolds like here. Okay, and that's how you just factor this whole expression out. Again, you're just making this ansatz right here that I know what F looks like, and then let's see how that pans out. Okay, so the way you then think about this differential equation, right, is that Reynolds is the thing that I can vary, and independent of what the F's are, right? This is my dependence, right? I vary R, and I just say F0 and F1 can be their functions. The only independent parameter here being the RE, you setting it equal to anything, okay? So this you could think of, right, as order 1. Right? For this to be equal to be 0, independent of any Reynolds that I choose, that certainly means that this expression right here, which is the order, let's say, 1 term, this must be equal to 0 for all eta. Same thing that happens here, right? The way this is working, if RE, if my Reynolds number is the only independent parameter that I have to choose, and this has to vary, that would mean that this term right here must be, which is really the order Reynolds term, this must be equal to 0 for all eta. And then it just keeps on going, right? Here's the order Reynolds squared. So these are all very, very tiny numbers. These as well must be, right, equal to 0 for all eta in the domain. You see what you've done now? What you've done now is you've taken your hard problem and you've broken it up into simpler problems. Okay? Instead of solving one differential equation, I now solve a bunch and then add up the results. Seems trickery though, right? And it is trickery, right? You're modeling it like it's a linear problem, but it's not linear. It's a nonlinear ODE. But somehow you're adding up solutions to get the effect. Okay, so now I just have a bunch of differential equations. And the same thing is, don't forget to do the exact same expansion for the boundary conditions, right? So what the boundary conditions look like is f of 0 was, right, the 0th order plus Reynolds plus 0. This is equal to 1, and then think about it as r times 0. Okay, so now these boundary conditions, what they say is, okay, so now the boundary conditions for the 0th order set are this. And then for the 1f, it's 0. And similarly, you have this for symmetry condition. And then here, same thing. This is now 0, 0, 0. Okay, so you do, right, you sub that expression in for that series, and what you get, right, is these, right, and you get differential equations. Now I've written out the 0th order differential equation. I've written out the first correction term, which I'm trying to figure out what this function is and what these functions are. And now you have new differential equations. Essentially, this term being equal to 0 forever, this one being equal to 0 forever. And then you also need to assign to those differential equations boundary conditions so you can get a solution to them. That comes from here too. Everything comes from the onset of the assumption that the function solution looks like this. I said many times before, the only way any progress is made in differential equations, it seems like, is if people just assume what the heck the solution is going to look like and then plug it and chug it through. Okay, so the 0th order solution, the 0th order one, has a solution. You can do it by a bunch of substitutions. Okay, so f naught, I don't want to check it again, looks like this. Our small Reynolds. Right, so this is the 0th order one. Okay. Now notice this is just from applying things. Now I know, right? So now you really know what the f00 is. And now you can solve for this one, right? Because now the differential equation for the first order, or the correction term, looks like this. Okay, so this is the solution for the 0th order one. You can figure now out what f1 is because because these are just f1 values, right? You know what they are now. It's really rough because you have to plug this in there and take a derivative, and now this differential equation just looks like it has a forcing term in front of it and it has boundary conditions. And then this also has a solution. That solution is really large. Okay, it's very, very large. But it can certainly be coded, and you can certainly then plot out, right? You can make these plots of what the velocity profile looks like, right, for small Reynolds numbers. Because RE has to be very, very small for this to be true. I mean, if the Reynolds number is like 0.8, then that means that this expression right here does matter quite a bit. But if like the Reynolds number is 0.3, well, then that means that this is like not even 10%. So don't get rid of it. So usually a good rule of thumb with these asymptotics, right, is think about this as really like you really want, for the first order to matter, you really have a limiting thing of you want the, right, you would need the Reynolds number to be less than 0.3 because the square relationship gets you 10%. Okay, that means 10% difference on this term here. But you could plug it in, and you could plug it in, and you can draw what the velocity profiles look like, and you get really exactly what we had thought, right? With my, yeah. So then, if this is going to be my f, and then here's the eta, and you have it looks like this, and then really, it goes to 0. Yeah, it goes to 0. And then you just really sort of have the dependence of these Reynolds things going like here. This is a really small scale, so it's hard to. Okay, these sort of blown up so you can see it. And then for a Reynolds number that's positive or negative, right? So the negative Reynolds numbers take away from the plot, so it looks like this. But importantly, they really kind of just look like quadratic profiles, right? I mean, really like the f. I mean, if you look at these things and you just take this expression right here, this really even looks like an eta squared term. It's great. It's great. So now you've encapsulated this small Reynolds number to first order by this trickery method I've just shown you. And what's the method? The method of approximate asymptotic solutions is, for now, if you're not an expert in it or just seeing it for the first time, you say like, okay, there is a small parameter in my differential equation. If I know that that's really small based on parameters that I've measured and know, I'm going to assume I know what the solution looks like. I will then plug that into my governing differential equation to get 2 ODEs to solve. And if I can solve that, I can actually write down analytical formulas which completely tell me how the parameters are coming up. Right? Essentially what you've done is you've assumed the Reynolds number dependence to the solution. You didn't really solve for it. Right? This idea that f looks like this type of a series is saying, I know how Reynolds numbers affects the solutions. I'm assuming it just looks like this series where Reynolds gets smaller and smaller. So all the effects are really pushed up to the front right here. And what the solutions then tell you is then how the angle is affecting the solutions. Right? So now you have wedge angle really being the dependence. Right? So any wedge angle now I can plot. Right? For any wedge angle, I can really plot you what the velocity profile looks like. So then this is like you would have different ones. This would be for a 10 degrees. You could plot another one for a different eta, for a different alpha, etc. But for these small alphas, right? For these small alphas, it is right. It's nice to have what the Reynolds number dependence is. It's nice to have this f1 and plug it in there with Mathematica and solve for it. But really, this is the important plot that you have that tells you, like, if I have really slow flow and it's inflow or outflow, you'll get these situations. Okay, so that was for the case of Reynolds number being very small. It looked like that. How do we handle Reynolds number being very, very large? So that's that case of the inertia-driven flow in Jeffrey-Hamel wedge flow. Right, so this it was almost a bit easy now for Reynolds number to be really small because you just killed out the nonlinear term, okay? Negative infinity, right? So how do I want to categorize that impinging flow really, really fast towards the center, right? How do I get that? Now this is a great term to really show you, right? This is the sort of situation where you see how this scaling for these things, or boundary layer effects happen in these differential equations. Okay, so let's do this again. So dividing then by the Reynolds number, now I have this. Okay, because if Reynolds number is blowing up to infinity, I can sort of do the exact same situation that I had before with a small number, because now this is a tiny number and this is a tiny number. And the magnitude blowing up. So very, very fast flows. Now it looks like this. So one way to think about it is you could just now have epsilon terms here. Right? This is just your 1 over Reynolds number now being your very tiny expression. In this situation now, it's like you've just had these epsilons. But this is the problem now. And the problem now is when you do this one, you now have, right, now you have your small number on your highest derivative term. So that's called a boundary layer problem in asymptotics. It's called a boundary layer problem because it means, right, if this actually goes to 0, the problem just looks like this. But the problem with that 0th order solution, right, is it's not even related at all to what this third order solution would look like. You know, when we do when you do asymptotics, right, you could have like it works even for algebraic properties as well, right? So if it had finding the roots of this equation, like let's say even with to the 4th. So let's say you couldn't actually factor this out, but you have this parameter epsilon to play with, right? You could do this same thing where you would go like, okay, so how about my x, my root, right? If you could say that the root here being 0. So in this situation, when epsilon is equal to 0, so the 0th order term right here, right, if this goes to 0, now this is an easy problem to solve. I have x to the 4th equaling here. So that would mean I could have, like, okay, well, I have, right, so I have 4 roots, right? So I have these 4 roots, and they could look like this. So then for the second order, you then do the same thing. You would plug everything back in and yada, 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 yada. But when you have like a polynomial like here, same one, okay, so now this is a small number. Now, right, now when epsilon is equal to 0, now the issue being there is now now it's 3, and it's only there's only one of them, right? So before I had 4 roots, and I could figure out the 0th order term had all 4 algebraic roots in there. And then for this situation, when this goes to 0, notice that I just have 1 root. I don't even have 4 roots anymore. So these are called singular perturbations. There's an issue essentially coming from the fact that my small number is in front of the highest order derivative term. When that is the case for this type of stuff, you have to rescale the equation so you can get it out of there. That's your goal, right? So the problem being that when I do this large Reynolds number and I divide out by what the Reynolds number is, I have now a small number on the highest order derivative term. I have to get that term off by a rescaling. Okay, so what's going to happen with this rescaling, right? Same type of thing where in Jeffrey-Hamel flow, if it's really, really, really fast, okay, very, very fast, it all just looks like a radial plug flow, but there's some very tiny, right, viscous regime right here happening. Okay? There's some little sweepy bit of angle where the viscous force must matter so that I can obey no slip when I get really, really close to there, right? Okay? Essentially, if you made like a plot right here, what's happening in the differential equation here is if here is my eta and here's the f, right? If you're really far away, right, if you're zoomed very far out, the function just looks like this. It just looks like a constant function, right, you have here. It's going so fast that all, right, it's a very inertial flow, it just looks like this. But the problem is your scale right here is just too frickin' large. So the idea being, actually, if you zoomed really close up to right around where 0 is, because here's where eta is equal to 0, where I have to obey no slip, right, here's eta equal to 1. Okay, what's happening is from a very, very far distance, it just looks like here in your mind's eye. But in a mathematical zooming process, what's occurring is it actually is 0 right? It just almost looks like a step function. But if I zoomed really close into here by some other length scale, you could actually see how that effect's happening. Okay? What that means is almost like if you took some infinitesimal magnifying glass happening right here, okay? So here's what you're going to do in this solution behavior right here. Again, this one, right, this, why am I saying that it looks like a constant function, right? I'm saying that because when epsilon 0, these terms drop out, and now I just have 2 alpha equaling 0. Do your same trickery. I mean, this goes to 0. This looks like 1/2 d equals to 0. Do your little trickery thing right there. So this means that, right, this has to equal a constant. So this must equal some sort of constant value. But the boundary condition, right? But the boundary conditions say, well, I know it at one value, so that means that the function must be just that constant. So that's why I say this looks just like the function 1. Okay, that's why I'm saying it's just a constant function. Because when this is actually a 0 or small value, it just looks like 1. Here's this thing, though, right? The idea being, I know it has to obey no slip, so there's some very tiny scale right here. Right? Some tiny region of values where this has to be true. Okay? And if I zoom really far in, then I could see it. Okay, zooming pretty far in here, now what did look flat, now I can start to see that curvature. Okay, and this is 0. So this coordinate now is not eta, but some magnified up version of eta, right? Some zoomed in scale, really, really close into here, right? So some tiny scale, I'm going to call that C. So here's the eta dimension. It goes from 0 to 1. But this coordinate psi, right, C, right? This is very, 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 right? This is an extremely tiny number, right? So in reality, this is almost blowing up to infinity, right? Right? Measuring the scale on this dimension, right? If I measuring the scale on that length scale, one looks like infinity to you in the C scale. So this idea of what is that length scale? Mathematically, you can figure out by a scale argument. We can also kind of get there, actually, amazingly, just from some physical arguments. Okay, so have that one. So what's the viscous length scale? What's the viscous length scale? What's the viscous length scale? Okay, so we already showed in the vorticity thing, right, that this is the square root of this nu and then a time scale right there. Okay, moreover, right, you did this d here, and then I have, what was it? Nu over the delta, right? So this one right here, this being the viscous diffusion velocity. How fast, right? How fast is vorticity diffusing into the flow from the wall? That was this relationship right here. Okay. So what scale are we looking for? That's this triangle that we get. Okay, the triangle we get right here. If I'm at the wall, okay, so this is really, I flipped it over, so now I'm just looking at myself right close to the wall there. Okay, here's this. Very tiny, something like that. Okay, there's a triangle here. Right here is my tiny distance, beta, right? So similar again, right? Imagine, right, this is restricted to just being, right, here is alpha. Here is this coordinate theta, and I'll call this thing beta, such that alpha is really the sum of my theta coordinate, the order 1's one that I had, and then this beta angle. So this being the length scale here of the angle, non-dimensionalized not yet. So this is really saying there's some scale in my independent coordinate that looks like this, and then this one here. This one looks like it's just ranging from 0 to alpha, and this one looks like it's ranging from 0 to an extremely tiny number. So then right here I have, okay, well this is the velocity inward, so here's my v. Our triangle says then that this, I'll see right here, should look then like beta okay, and then sine for a very tiny number just looks like sine, just looks like the value beta, right? So then this there, what else do I have there? That's it, right? Yeah. And then you get that, so for this psi coordinate, I know that, what was my, okay, so then beta over alpha or the Reynolds number comes in because of how we defined it earlier. Where's my definition of Reynolds? Yes, so Reynolds number. Remember, we had the definition that this was sort of my scale velocity and alpha and r from there. So there's this scale of this 1 over alpha. And then you have to use the wall variable as well. Okay? So by wall variable, what I mean here, so this is just some magnification scale that comes from the viscous diffusion, right? So if this is the radial component of velocity, right, I can get this, right? I get this d, right? I can get the inward or the diffusive velocity of right, the vorticity diffusion velocity, right? And I just relate that to the component towards the wall using trigonometry. And then that value being very small, I can solve for what the beta is. That definition of Reynolds has this, that this is the scale of that tiny number. Okay? And what I mean by wall coordinate then, right, is by wall coordinate, I saw this equation, right? So alpha over alpha would be equal to an eta because I have a theta divided by an alpha being my eta value. And then this beta right here is the c. Right, so this is just 1. So then this is the idea that c is the so that's your c. And it comes from this idea that I have to magnify this, right, by the Reynolds value itself. So if I take 1 minus eta, right, when I get down to there, I have to blow that up by a Reynolds, by square root of the Reynolds. Remember, Reynolds is a very large number for us right now, right? It's a very large number. The magnitude of it's blowing up to infinity. There's a little trick. You just define it. You write the negative of a negative being positive, and then it works out. Well, it works out. Okay. All of that to just rescale to a new independent variable. Okay? So what that means is now that you have this new independent variable, right, I'm saying here's a side equals this, right, normalizing ratio. Right? I just now plug this into this differential equation. Plug that into that differential equation, and then figure out what the f of psi is, or my new wall variable, and you get a new differential equation that's scaled properly. Then I get okay. Now you notice I got rid of that tiny term in front of my highest order derivative, right? Because now this is a deep psi, and these were d psi, and this was a d eta. So the eta, the problem was using my differentials in terms of eta, I can't see that no slip condition happening. But if I take a 1 minus the eta and scale that up by the Reynolds, now I can start seeing it. Notice that when, right, the 1 minus being important because that's being this area right here. Right? Oh, it should be 1. Very sorry about that, right? You have to think this is sweeping back up to the wall. So this being actually the 1, and that being the 0, right? So when eta is very close to 1 or really close to the wall, this, right, now you're getting towards this area right here. So as eta gets really, really close to the wall and no slip should be happening, I get to now scale up my independent variable by a square root of the Reynolds and the alpha term itself. And that comes from this viscous diffusion length or vorticity diffusion velocity thing happening. So now you have the more properly scaled equation. It comes with boundary conditions as well. What are the boundary conditions? Well, for these ones, we do have the correct boundary condition. Now I can say that this at 0, right, no slip, right? When eta is equal to 1, I'm at the wall, right? So eta equal to 1 being at the wall, that means that this is 0. So this can obey no slip, and that's going to keep the order derivative term here. And then you also have now limit terms, which are just sort of satisfying what you would expect, right? And that is when this coordinate is blowing up far, far away to infinity, right? Or as I'm approaching this 1 value, I have to look like 1. And then slope derivative. Okay, and this is the symmetry condition. This, with respect to this coordinate right here, it's got to go to 0 as this scale is blowing up to infinity. And now this is a good system and has a solution. Okay, so what do we have? So this one right here was that outer solution, which was very simple. It was just 1. Now I'm on the hunt for the red line, the F inner. Right? Or I could think of this as F as this. What does that function look like? That obeys this differential equation, and this one has a solution. Okay? This has a solution, and you get it by doing a tan h squared trick. But this one I'm OK if you look it up. I like getting this one on my own, too. So if you want to know how to solve nonlinear differential equations, take your favorite problem and just see how you would get that. That's how I did this once, and it's fine. So the inner one okay, this is a solution then. It's a square. It's a tan h squared relationship is going to be in there. And then there's this arctan, and then you have it's a very, 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 very pretty solution. And there's no problem with this. This completely characterizes this getting smaller and smaller and smaller. In fact, it really even shows you this type of profile here does have that relationship you have, right? Whereas the flow now gets faster and faster, you're just squeezing this up closer and closer into that wall, right? Where now, right, as the Reynolds number increases, right, as the Reynolds number is increasing in this type of situation because of this coordinate right here, now you're squeezing it closer so it looks more and more like plug flow. You're shrinking this scale. So this is the inner. And if you remember this idea, right, if you remember this idea, we did this before. Well, I want this thing to be valid uniformly. So for a uniformly valid solution, you have to take your outer uniformly valid solution. And you get this idea that if you didn't minus off one of the commons, you would double account for them. Okay? And the common part is the equality of these two things in a limit. So it's just that simple and unimagined, right? The idea is when the outer variable, so the common part being limit okay, these things have to match. And what they match to is this common part. Now, certainly, this inner part's just the value, right? This outer part's just the value 1. And then the limit of this thing as this die goes to 0 actually also ends up being 1. So that's the common part. So this inner part is actually just the solution, dependent on all the orders of large Reynolds numbers. Then you get wonderful plots. And you can see just exactly that dependence now on the inward. And then you have major issues with this if your Reynolds number was positive in here. There are issues, yeah, so there's issues here. If the Reynolds number becomes positive, there's a swap in a sign in the differential equation which shows that it doesn't work out. So you recover all that analysis of the quadratic under the integral. And the more important part is you can just go deeper and deeper on this thing, on this Jeffrey-Hamel flow. You can write this. It has an example of an asymptotic series where you look for the scales happening in the boundary layer that get close to the wall. I already showed you that, but you can do it more. Right? It shows you that nonlinear ODEs can be solved by fancy trickery. It shows you that the approximate solutions are given to you by asymptotic expressions where you really assume how the Reynolds number plays into the solution itself. And then you just derive new equations to solve with new boundary conditions. It shows you that implicit solutions can still tell you something about how parameters affect solutions in a more educated way. If I never wrote out that implicit integral, then I wouldn't know how to plot a relationship between alphas and Reynolds to see where things could go wrong. So it's certainly a faster computation and certainly a faster parameter sweep for you to do. But more importantly, you just keep on going on this problem. And whether you learn anything about the math tricks at all, I think it's better to just see how deep and how many questions you can start to ask. Okay? For these large Reynolds numbers, you're even recovering the flow velocity, and you can plot them, and you can just see, okay, well, if I'm going further and further into the Jeffrey-Hamel flow, it looks like plug flow with boundary layers on the very edge, and I can go further in there. And if it's expanding flow, you have major issues given up by the 10.31 relationship that we had earlier from the elliptic integral. Amazing. This scale thing right here even has its own description, right? You did it through this physical argument, but you don't have to do that, right? Getting this expression right here, you don't even have to actually do the physical, right? The physical argument for it with that whole beta thing. I certainly don't do it. You actually could just look at it. The form of this has an issue, so I have to rescale my variable. How do I do that? This would just be then you going like, I know it has to look like this, right? What is some magnification, right, of an eta variable, right? right, this square root Reynolds alpha thing, that came actually from me going like, what's the viscous diffusion length of vorticity diffusing into the wall and get things. But it really is still coming from you balancing inertia and viscosity. Okay, so if you look for this balancing my wall variable and you go like, well, what is this magnification term right there? Okay, if you change everything to a thing of C, you would then have some scale relationship if this is going to be the one term, second term. This is the third term right here, okay? So then you just do some, then you, right here at this page, you just do a balance and you say, I want viscous forces to balance inertial forces at some length scale. Say it out loud. Okay, then you in the scale relationship, okay, and then comes right out there. Isn't that funny? I think it's funny, right? You do like, it's like, seems like it'd be a genius to like come up with like viscous, but it would just come from the fact of, oh shucks, I have some boundary layer problem where a tiny number is multiplying my highest order term. Well, you just go like, okay, I need to find a length scale of my wall variable, magnify it by some amount of term. Plug all this crap back in there and go like, I want my inertia term. This term came from the inertia value. If you think way back in the day for Jeffrey Hamel, it's like those are the inertial terms, and you had viscous terms having an effect. You go, find me the length scale m such that this term balances a viscous term. What does that mean? Well, physically, you're just really doing the same arguments that I did with the sine, something like that. You're saying, what the heck does this have to be such that I see the no-slip issue happening? No-slip happens because of viscous forces having to get down to a zero length scale. So you're just solving now for this m value, and you get the same relationship without any sort of physical argument, because just mathematically you're going like, shucks, 0, okay, rebalance. Let's rebalance according to some independent length variable. And then you get this. So it still comes out. Right, remember, there are trickery things here. If I said I had inflow, well, then I would have a complex number right there. Okay, well, you really just redefine something, right? If I have the RE, right? If it's going to negative infinity, you just sort of redefine it as the positive because you have a negative value. Okay, slight trickeries. It's more important than the magnitudes blowing up to infinity. Now, these issues actually of positive and negative Reynolds, I could just stop right now. The issues all coming from this positive Reynolds number in this approximation right here, if you kept the sign important, you would get complex issues happening. Now your differential equation would have now complex issues and complex variables. And then that branch points still then tell you the issues of this 10.31 coming out. And you can see it unfold in your eyes doing it that way if you want to do it. And then if you know what, I'm already way over. Clearly, you see, I just kind of like digging more and more and more into this thing. You know, it's really fun. But right, major point being, right, I like Jeffrey Hamel flow. I like that it shows all these methods for me of how to analyze a fluid flow and consider different concepts. I like how it has the asymptotic series that are in there because I'm trying to look for how Reynolds numbers have small effects on the solutions, big or small. I like how it's an example where I can see rescaling differential equations so that the highest order term can stay in there. It plays out as well. And then I like how once you look at these solutions and plot them on a computer, you can kind of see how someone would look at those velocity profiles and then maybe if they had no idea, go like, oh, I see, the inviscid part or the